Gravity is the force which pulls everything towards the center of the earth. It is also the force which binds planets to their stars and also the moons to their planets. It's an all-pervasive force seen everywhere in the universe. In this discussion today, we're about to discuss a very interesting problem, something that happens very, very frequently in our universe. This is the binary star problem that we are about to discuss. We will discuss a problem where we have two stars bound to each other by their gravity, rotating in circular paths about their common center of mass. Much the way you see these two stars rotate in the diagram. They are both rotating in concentric circles, and their center happens to be the common center of mass of these two stars. In the diagram that you see on the board behind me, you see two stars having masses small m and capital M. The two green dots that you see over here, they are two stars. The smaller dot is the smaller star with mass small m, lowercase m, and the bigger dot is the larger star with the mass capital M, or uppercase M as some would call it. Now, these two stars are located at a distance d apart from each other, and they now rotate about their common center of mass. Now, why is it that they rotate about their common center of mass? We are making a very simple assumption here that there is no external force acting on the system of these two stars. The assumption being that any other stars are so far apart, far away, that they exert no influence on these two. And if there are no external forces on this system of two stars, then essentially we have a system with no external force, and so the center of mass is at rest. When the center of mass happens to be at rest, that becomes the common center of rotation. Now, let's work out the location of this common center of mass. The total distance being d, let's assume that small m is at a distance r1 and capital M is at a distance r2. Now, we'll assume that the center of mass is the origin of the coordinates, and therefore the coordinate or the x coordinate of the center of mass will be 0. And therefore we calculate the center of mass, the location of the center of mass, as x equal to 0. Now that x equal to 0 happens to be small m times minus r1 capital M times r1 divided by m1 plus m2. Now this essentially means small m times r1 equals capital M times r2, and of course r1 plus r2 happens to be equal to d. Solving these, we get r1 and r2. As you can see on the board here, we've now calculated r1 as well as r2. We are now going to observe the mass small m, the star small m, which is rotating in a circle of radius r1, and we've already calculated r1 in the previous step. Now small m is rotating in a circle of radius r1, and therefore its acceleration towards the center of mass is omega square times r1, omega being 2 pi by time period of revolution. Now in one of the earlier diagrams that I showed you, both the stars were rotating with the same angular velocity about the center of mass, and that happens to be the case here. So we just need to calculate the time period of one of the stars, and you know the time period of the other. So let's go ahead and calculate this time period looking at star small m. Now the force of gravity on the star of mass small m is g into capital M times small m by d square. The distance between the stars is d, right? So that's the force there, and that equals m omega square times r1. Now let's substitute r1 in this expression, and we end up with this equation appearing on your screen. G capital M small m by d square equals small m into 2 pi by t whole square times r1, and r1 happens to be capital M times d by capital M plus small m. From here it's a simple calculation, and we get the time period t of revolution of this star here, and that's your time period t, 2 pi root d cube by capital G times capital M plus small m. A very exciting problem, and yet a very simple one, this binary star problem. So that's your beginning of problem solving using Newton's law of gravity. We will keep bringing more such problems for you in the time to come, and perhaps in the next video I will introduce a tri-star problem, which surprisingly is simpler than the binary star problem. So that tri-star problem comes up in the next video. If you learned something here today, please consider subscribing to this channel. Keeps me encouraged to do more and more interesting work. Bye bye from me. Thank you for watching this.